So does anyone have any questions? Okay. So we'll start. Let's start with the review of our previous lectures discussion. So in the last class, I had started talking about critical state theory. So, we are really looking at slow flows. So these, you can imagine that, the system is densely packed, and so all the particles are in contact with each other. And then when you try and deform them, as they deform, there's no force between the particles, and that force is entirely due to friction. So it's a friction dominated flow. And the first approach to try and analyze these flows is through just assuming that the material is at the point of yield, use the Mohr Coulomb approach, and then you can get quite good results. And we saw, for an example of flow in a wedge-shaped hopper, that in fact this theory works quite well, because I showed you even the results in comparison to the exact numerical simulations using DEM. But in that theory, the main issue is that density is a constant. Whereas if you look at this critical state theory, it takes into account changes in bulk density. Okay, and also we'll see that it's independent of the relative velocity. So friction forces are taken into account properly. Then, we can imagine that as bulk density increases or decreases, this will depend on the stress. And at the critical state, there is no change in bulk density. So, once you reach the critical state, then the rate of change of density is 0. And this is what we saw in the previous class. So we just looked at what is the approach to a critical state. So for this critical state theory, we need the yield function, where sigma 1, sigma 2, sigma 3 are the principal normal stresses, and rho b is the bulk density. The second condition is that the principal axis of the stress and the principal axis of the rate of deformation tensor, where d is just gradient of v plus gradient of v transpose divided by 2. These two principal axes are collinear. That means they are in the same direction, along the same axis. And then we also have something called the flow rule, where di is just lambda, which is a constant, times the derivative of f with respect to the sigma I, where sigma I is of course principal stress, and di are the principal components of d. So these three will define this critical state theory. And as I said over here, it takes into account changes in bulk density, but also it takes into account the fact that the flow is friction dominated, so the force is independent of relative velocity. So both those things are important. And in the last class, we spent the whole class trying to understand at what point we reach the critical state. So for a typical yield function, this is a yield function in which is given by f is equal to 0 for a 2D system. And of course, in this also, this is for a particular value of the bulk density. So let's say rho b is equal to rho b1. And we saw that there are two vectors. One is d, which is along the diagonal, and the other is n, which is normal to this line. And by doing a little bit of geometry, we saw that the slope of this, which is just equal to the ratio of the components of the normal vector minus of that, because you know that this vector and this vector are normal to each other. So this is connected by -1. And that is directly related to the partial derivatives of the yield function with respect to the principal axis. So this is one relationship we got. And then once we use the flow rule along with this, because we know that this ratio is given by this, we actually got that n1 by n2 is equal to d1 by d2. And then from the continuity equation, we showed that the rate of change of density is related to just v1 divided by n1 into L, where L is just n dot d, which is the projection of the vector n on the diagonal. And from this, we can see that when L is greater than 0, you have dilation, that is, the volume increases and the density decreases. And when you are in this region, you have compaction, that is, L is less than 0, so the material becomes more dense. And of course, when you are at the critical point, that is the point at which the normal vector is normal or is perpendicular to the diagonal vector, you are at the critical state where there is neither compaction nor dilation. So we saw this in the last class. And now what we want to do is, I'll do a couple of examples, but the main example is to do exactly the same problem that we did using more Coulomb, using this critical state theory. And then we'll see, some practical issues related to bins and hoppers, that how can we really calculate the mass flow rate and so forth in these systems. Okay. So today, as I had mentioned, there will be a quiz which will happen around 11:15. So at around 11:10, I will stop. If I'm going on, then just let me know and I will stop the. Okay, so we had done all this and we had come up to this point. And what I'd like to do today is 9th of September, and today we are in lecture number starting.
Sir, your tab screen is not showing.
Yeah, I will just share it. Did you see the presentation you could see?
Yes, sir. Presentation,
Okay.
I could see.
Now is it okay? So this is what we were looking at last time, all these things on how we can use these equations to show when we will get the critical state. And so let's now, that was in general. Now let us just look at a very specific example. And let's see. So I want to look at an example for which, and I'll use this same, so that is, supposing we are given a particular yield function. So can we find out the critical state for the yield function given by f is equal to tau max minus sigma c sine beta into n alpha minus n minus 1 of alpha raised to the power of n divided by n minus 1. So this is the yield function f, and this at the point of yield is equal to 0. Now you say, oh, what is this tau max, sigma c, and alpha? Okay, let me just put this down. More definitions. Alpha is, of course, sigma m by sigma c, and sigma c is given as a exponential of minus b divided by rho b. Okay, so you can see that this is a yield function, and what are the parameters here? So the parameters are basically n, a, and b. So sigma c is some kind of critical stress, and a and b are how the density is related to the critical stress, and then n is another parameter which defines this. So if you see this, your f now here, if you see this f is actually tau max, it's a function of tau max, sigma m, and rho b. But we know that what is tau max? Tau max is nothing but sigma 1 minus sigma 2 divided by 2, where sigma 1 is the maximum principal normal stress, sigma 2 is the minimum normal stress, and sigma m is just equal to sigma 1 plus sigma 2 divided by 2. So if we substitute like this in this equation, then you can see that what I've given you is f of, that is, whatever I have given is exactly equivalent to sigma 1, sigma 2, rho b is equal to 0. So they are equivalent, only thing the nomenclature is a little different. Now we'd like to find out what is the critical state. And you know what we have already seen from the class last time is that at the critical state we have del f by del sigma 1 divided by this is equal to n1 by n2, and we have also seen that n1 plus n2 is equal to 0 at the critical state because n dot d is equal to 0. So what we have at the critical state, we have that n dot d is equal to 0, and this gives us that n1 plus n2 is equal to 0, because, okay, so I can write it down. So n we have seen is nothing but n1 e1 plus n2 e2, and d is just equal to e1 plus e2 divided by root 2. So these are both unit vectors. n1 and n2 are the unknown components of the normal vector, and they have a magnitude equal to 1, and d is a line along the 45-degree line over here. So that obviously e1 plus e2 by root 2, that is what it is. So you can see from these two that if we take n dot d, that we are taking the dot product between these two, then this is just equal to n1 plus n2, and then from the class last time we saw that it's equal to 0 at the critical state. So the sum of the normal components are equal to 0. This implies that n1 is equal to minus n2. And we have already seen from the previous class that n1 by n2 is just the partial derivative of f with respect to sigma 1 divided by the partial derivative of. So this essentially gives us that. So from the previous class we have n1 by n2 is equal to del f by del sigma 1 divided by del f by del sigma 2. But since n1 is equal to minus n2, so this is equal to minus 1 at the critical state. So now we can find out what is del f by del sigma 1 from this formula that we have been given, and del f by del sigma 2. So what is del f by del sigma 1? Well, we can, since we know this in terms of tau max and sigma m, we can write this as del f by del tau max into del of tau max by del sigma 1. So, this is just using the chain rule. So here we can calculate all of these things, but the main thing is that you see del of tau max by del sigma 1 is just half, and del sigma 1 sigma m and del of sigma m by del sigma 1 is also half. So this actually just simplifies to half of del f by del tau max plus del f by del sigma m. So this is the first result. Similarly, we can do for sigma 2. And this is equal to, again, same thing, same formula, but instead of sigma 1, we'll write sigma 2 Okay. And again, if we look at this formula, if we take the derivative of tau max with respect to sigma 2, you'll get minus half. And with respect to if you take off this with respect to sigma 2, you'll get plus half. So you can see this is nothing but, again, half comes out. But for this, I'll get minus 1. So it's minus del f by del tau max. And then you'll have plus del f by del sigma 2. So this is one of the things. Now, if we look at this formula, look at this formula, then you can see that del f by del tau max is just equal to 1. And if you look at what is del f by del sigma m, well, again over here we can write del f by del sigma m can be written as del f by del alpha into del alpha by del sigma m. So it's just connected by a constant. So del alpha by del sigma m is just 1 by sigma c. So this is just 1 by sigma c of del f by del alpha. Now let's look at this. If you take the derivative of this with respect to alpha, then what do you get? So you get del f by del alpha is equal to, the first term will go to 0. This is just a constant. And then here, when you take the derivative with respect to alpha, you just get n. And from here, when you take the derivative with respect to alpha, you will get n into 1 minus n. So let me write this down. So this is equal to minus, why don't I do something clever? I will write down this function one more time, which is really not a big problem for me, because I can just do copy and paste. So here we have the function again. So it becomes easy for us to take the derivative of this with respect to alpha. So here you have del f by del alpha. The first term, this term, 0. Then you just left with this. Sigma c is just a constant, so minus sigma c sine beta. And then we take the derivative over here. This is just n minus n minus 1. And when we take the derivative of this, we will get n divided by n minus 1 into alpha raised to the power of n divided by n minus 1 minus 1. So when you simplify this, this just becomes minus n sigma c sine beta into 1 minus alpha raised to the power of 1 divided by n minus 1. Because you do, if it's, this is n minus 1, so it's like n plus 1, n minus n plus 1, so that is just 1. So this is what you get. So this is my result, that when you do df by d alpha, you have this result. Now let's just go back here. We have already shown that this ratio is equal to minus 1. That means if I take the ratio of this to this, it should be minus 1. So we have but we already shown that this is 1. So what we have is 1 plus del f by del sigma m divided by minus 1 plus del f by del sigma m is equal to minus 1. So if we simplify this out, what we will get is, we will get that del f by del sigma m is equal to 0 at critical state. So I have not done the algebra, but if you cross multiply and then you collect terms, you will see that 2 times del f by del sigma m is just equal to 0. So this is equal to 0. So this actually gives us, since we know that del f by del sigma m is just 1 by sigma del f by del alpha, so then that also gives us that del f by del alpha is equal to 0 at the critical state. And when is this equal to 0? So this implies that alpha is equal to 1. From here we can clearly see. So you get a very nice simple result that alpha is equal to 1 at the critical state. So what is the definition of alpha? Alpha, if you see, it's just the ratio of the mean stress divided by this critical stress. So at the critical point, sigma m is equal to sigma c. So this is what you have, that the mean stress must be equal to the critical stress at the critical point, at the critical state. And then, you can even find out what is the yield point. At the yield function, what does it become? Well, here is our yield function. So if you put alpha equal to 1 over here, so then, if alpha is 1, then this term just becomes 1. So at the critical state, your function f is just equal to tau max minus, now over here you see f is minus sigma c sine beta. If you put this alpha is equal to 1, then you'll have in brackets, so that will be n minus, now here you have n minus 1, and then of course alpha is 1, so raised to the power of n minus 1 is still 1. So this is what you will get, and this is equal to 0. And so this gives us that tau max is equal to, just see from here, n minus n cancels plus 1. So this is just 1 inside the bracket, just turns out to be 1. You take it to the other side and I'll get. But we already know that sigma c is equal to sigma m. So this essentially gives us that tau max by sigma m is equal to sine beta at the critical state. Is this familiar to you? You will see that this is nothing but the Mohr Coulomb yield condition. At the point of yielding, sine beta is just tau max by sigma m. So we have done this simple example where we took a particular value of a particular form of the yield function, and then we were able to find out what is the condition for the critical state. And what we found out was that for the critical state, this parameter alpha must be equal to 1. And then we also showed that when you are at the critical state, the yield function simply reduces to the more Coulomb yield condition. Now if you plot this yield function, what you will get is something like this. And so this is F versus alpha. And so you'll get the maximum over here, and this corresponds to alpha equal to 1.0. And like this, you can plot many of the other curves, and at each point you will have essentially alpha equal to 1, and hence you will essentially satisfy the more Coulomb at the critical point. So this is the key feature of the critical state theory, that the yield function depends on the density, but once you're at the critical state, what the yield function gives you is exactly equal to what the more Coulomb yield condition would have given. So, the main point is that the critical state theory doesn't contradict more Coulomb. We have seen that, in fact, more Coulomb works very well, especially when you are in nice steady state conditions. But when you deviate from those conditions and your density is varying a lot, then you can essentially generalize it to this critical state. So the next thing that I want to do is, now that we have some, so I would like to do one more example, and I'll just introduce it here, and then slow flow in a wedge-shaped hopper with radial gravity. So I will not write it all over here. So this is a same problem, but what we are going to assume is radial gravity, as we had done before, frictionless walls, but we can have a varying density. So this part requires us to use the critical state theory. So we will see now how we can apply this. And what we'll use is the yield criterion same as the previous example. So we'll use that same yield condition, and then what we'll see is how we can actually simplify all the equations, including the coaxiality condition, the flow rule, and so forth, for this problem, and how we can actually come up with enough equations to be able to get a solution for the problem. Okay, so we'll do that in the next class. So again, can we do exactly the same as what we did for the previous quiz? And I'm going to essentially leave this meeting, and I'm going to start the meeting for the two groups.